Hi, everybody. So as Liz said, I'm the developer evangelist for Qualcomm Vuforia, and Vuforia is Qualcomm's mobile vision platform. What we do is to take advanced computer vision algorithms, we refine them into useful features for handling images, objects, and environments, and we deliver those to developers as a set of SDKs and easy-to-use workflows. And so the feature that I'm going to be talking about today is Smart Terrain. Smart Terrain is a technology that enables you to actually reconstruct your physical environment as a 3D map, as a set of 3D meshes that distinguish between surfaces and objects in the environment. So in June, we had introduced Smart Terrain for standard device cameras, smartphone cameras. And this was really a breakthrough technology that what it's providing you is, in like a tabletop experience, the ability to construct gaming applications, product visualization applications that actually they provide a spatial awareness of your environment and an intelligence to interact with objects and surfaces based on their dimension, their physical arrangement, and their shape and their spatial orientation. Basically, it reconstructs the geometry as 3D meshes. So that's the proposition. During this year's keynote, we announced the support of depth sensing hardware using Smart Terrain. And the distinction between a standard device camera and a depth sensing camera is that a depth sensing camera provides the information necessary for us to infer the distance from the camera to a physical surface that's being viewed in the camera frame. A standard device camera, we can do that, but we need to impose a few requirements on the developer and the user in order to infer depth. A depth sensing camera enables all of that to happen automatically, so it's a much easier user experience and a much easier development proposition as far as creating apps using depth sensing hardware. So what I'm going to do today is talk about the feature, right? What is Smart Terrain? What does Smart Terrain actually do? I'll review Smart Terrain for standard device cameras, the version that's available currently, and then talk about some of the advantages that are arriving with depth sensing hardware. And currently we're supporting two devices that have come out that we've developed demos for, and that's the Tango device, which is by Google, and also the Aquila device by Flextronics, both of which incorporate IR-based depth sensing. So the consideration of using a standard device camera is that there are basically there's environments that we support, there's certain cases we support, there's certain limitations on it. It's an effective technology, but as a developer, there's certain things you need to know when you're developing for Smart Terrain using a standard device camera. The first is really talking about the supported environment. So what you want here is a setting that has consistent lighting. We really recommend something that has visibly discernible edges to it. We talk about it as a tabletop experience, right? So this is really relatively near-range experiences, sort of television viewing ranges. And what you're doing is really staging an environment that has a flat surface, ideally. And on top of that, you can place objects that we call props. And there's a language that we've introduced here in talking about how you're actually setting up the user experience for Smart Terrain. The tabletop, the flat surface with the edges, is known as the stage. The stage should be geometrically stable. You want something that's not going to start changing, it's not going to move. And the props that you use need to have some pattern of contrast variation on them. There needs to be details on the surfaces of the props so that the camera can pick them up, basically. And the other requirement with this really is just that you're not moving anything on the surface after it's been reconstructed. So there's really a user experience that's entailed where the user comes in, they capture the environment, they pull back, and they start reconstructing it. And at that point, the environment needs to remain stable. So if you're changing things, it actually changes the meshes that are created and it destabilizes things. Another of the requirements in using a standard device camera is that you need to use an initializing target. Now, as I mentioned when I was talking about depth sensing hardware has an ability to provide information that gives you scale and depth automatically. If you're using a standard device camera, what you need to do is actually bring in a known target of a known dimension. And what that gives you is really a ground truth reference. It gives you a reference for the scale that you can then extrapolate to the broader scene. So where we have the can highlighted there, what we know about the can is that it's 6 centimeters across. And we use that dimension to infer what the other relationships, the spatial relationships in the scene, approximate to, basically. How far are things from each other? How big are they? So the neat thing about it is what you're going to get from this is the map that's returned, or the meshes that are returned, are going to tell you what the dimensions of the objects are, what their distances are, and what the broader area of this primary surface of the stage is. And the other thing that's necessary in getting into this when you're building out the environment, when you're reconstructing it, is that you come in, and there's really an assumed user behavior. You come in, you initialize off of the known target, and then the user needs to pull back to bring things into the field of view with the camera, and they need to move the camera back and forth a bit. And what that's giving you is multiple perspectives on the stage that you've set up, and it enables you to get a better approximation of the spatial geometry of that scene. And it's really just, it's like coverage with a standard camera, as you're just going around so that you can see around the corners, you can see the top and the sides, and it gives you an idea of exactly what geometry you're working with. So really the process here is the user pulls back, they begin to capture the scene, it builds out the primary surface, which is really that stage surface on the tabletop, and it then begins detecting the props. So you have the initial surface area, you have props that are being approximated. You'll notice that each of these are surrounded by a bounding box. One of the other things when you're talking about using smart terrain on a standard device camera is that it's not giving you a smooth geometric reconstruction of the shape. It's actually giving you a volumetric bounding box around it. So it knows the extent, it knows the height and the width of it, but it's not attempting to go in and construct all the nooks and crannies of the surface, basically. And also the primary surface is always going to be planar. The stage surface is always going to be constructed as a plane that's fitted to the surface that you've identified in your setting. And so we talk about this as approximation. So one of the distinctions, again, in talking about smart terrain for standard devices versus smart terrain for a depth sensor is that with a standard device, you're going to get approximate geometry. You're going to get approximate scale as well, but really the geometry is a bit less precise than actually the scale understanding. When you are using depth sensing hardware, what it's going to give you is a much more refined fitting of the mesh onto these surfaces. It's much closer, it's much smoother, it's a denser mesh that's being returned. So it's much more realistic to the contours of the surfaces that are being created. And I think the other thing to distinguish here when we talk about smart terrain is it's not just giving you kind of a dumb relief of the surface geometry. It's not just giving you it's not like a point cloud, right? What we're actually doing here is that we're distinguishing the primary surface from the objects, the props that have been placed on the surface, so that you can handle those in app logic independently. You can actually identify that green surface area versus the blue prop areas, and you can identify the props independently so that within your app logic you can say, turn all small props into hills, and turn all big props into mountains, or turn all big props into trees, and turn all small props into bushes, or something like that. So when you're rendering on top of them, you're actually customizing the app logic appropriately to the geometry and the size of the objects in the scene. So I'm going to talk about the depth sensing hardware. Now, again, we just introduced this the other day. Jay Wright had announced depth sensing hardware, the range of depth sensing devices that are coming out using IR, stereoscopy, and the other types of depth sensing technology that are emerging. And so once they become commercially available to developers following that, we'll begin introducing support for them within our SDK. Now, some of the big advantages of depth sensing in dealing with smart terrain or these reconstruction technologies is that compared to a standard device camera, you're getting automatic initialization of the stage area, meaning that there's no user motion required. There's no initializing target required. It's really just capturing the physical surfaces, the objects and surfaces that are in the environment without needing to stage anything deliberately or without needing to introduce a predefined target into that setting. There's no motion required, and it's providing you much faster and richer results. So you'll see that the reconstruction happens almost automatically, and you're getting simultaneously the surfaces and the objects in the setting are being reconstructed. You can move around them to get better coverage of the shape of those objects, but you're going to immediately start getting meshes back. You're immediately going to get a reconstruction returned. And it's also much richer, meaning that when you look at the mesh that's returned coming from a depth sensing camera, and the way that we handle that is that the polygonization of the mesh is actually much tighter, and the surface fitting to the contours of the shapes that are in there, of the props, is going to be much closer. So it's much more realistic, and it's a much richer result. And really the big advantage in that situation is that it's giving you much more creative freedom as far as how you choose to handle these. Whereas with a standard device, you're getting back boxes, and you can make inferences based on the boxes, how you want to handle big boxes versus little boxes, or where they are positioned in the scene. With depth sensing, you actually have the ability to start introducing analysis based on, let's say, computational geometry, where you're looking at the shape of something, you're looking at whether it has a constant radius or whether it has a variable radius, and you're treating that differently. And one of the interesting things, what we do, and this is available in the demos as well, is that you have an ability to start introducing physics to these settings. And what you're doing here is really applying colliders onto the meshes. So with our current technology, with Smart Terrain for a standard device, we have samples out that what they're doing when we're approximating any of the objects is we put a box collider on top of them, right? And so for the purpose of things like game logic, it enables you to go through and immediately, like within the Unity environment, which is a game development environment, to use Unity physics so that as you have characters moving about, you can recognize when they're colliding with objects and they can respond accordingly. And you can also introduce pathfinding into that, meaning that knowing where objects are in the setting and knowing their properties, you can actually implement artificial intelligence so that characters are navigating around the objects appropriately. Now, some of the other considerations in working with depth sensing cameras versus an infrared sensor is that just as for the mode of the depth sensing is that standard device cameras are using visible light. Right? So what we're really looking at is patterns of contrast variation. When we're running Smart Terrain on a smartphone, it's really looking at the feature points that are available within the apparent image of the scene. So it's what you would see as a human being. And really what we look at is, the pattern of contrast variation again. Now, using an infrared depth sensor, for example, what that's actually doing is this is known as an active scanning method or an active depth sensing method. It's actually projecting an IR laser, and then there's a separate camera that's tracking that. And that's what it's doing. It's essentially to understand depth, it's triangulating or coordinating those points and understanding where they sit on the surface of something and knowing the position of the camera versus the IR laser, it can make an inferences to the distance for that. So that's an active scanning method. Using a standard device camera is known as a passive scanning method. So again, the advantages of this is that it's faster, it gives you a richer result. And really what we're doing internally is we're taking the RGB, we're taking the depth map image that's created using the laser, and we're fusing that with our own feature tracking capabilities. And we're fusing it basically with an RGB image. So what we're doing is we're merging some of the feature-based techniques that we use with a standard device camera and exploiting the depth sensing capabilities coming from an optic-based depth sensor. So as I discussed, in working with the depth sensor, you have automatic initialization. And again, the significant thing about this is that the depth sensor is giving you richer results, they're coming much faster, and it's even easier to use than when you're working with a standard device camera. Again, with the standard device camera, you need to pull back, the user needs to translate the device. With this, there's really nothing required. And you'll see when I go into the demo that it really boots itself up automatically. It automatically starts generating a depth map, and it automatically starts giving you good results on what's returned there. So as you can see, this is obviously just a visualization. This doesn't come from the thing. But again, it's giving you faster results, and it's also giving you richer contours. So when you look at what's happening with the props and when you look at what's happening with the surfaces, they'll be much closer to a realistic, what's realistically represented in the physical setting. So I think the other thing to sort of talk about as a developer consideration here is that you really have two artifacts that are coming back from the Smart Terrain engine. And one of them is reconstruction, which is distinct from the reconstruction of the objects or the props on the surfaces. So the surface reconstruction is always going to be fitted to a plane, right? And what we talk about here is this is referred to as the primary surface. It's really the stage surface that you're using. And again, even with depth sensing cameras, what you want to do is really identify a visually distinct flat area that you can use to stage the application or the experience that you're running. You can have contours on that, but it's helpful to basically be able to identify a coherent flat planar surface. And the purpose of that is that it gives you a registration point really is the basis of the scene, but it also tells you really what would you say, the absolute depth of the scene, how far you can go as far as implementing app logic or physics, what is the furthest point in the scene? And that's really the ground layer. And so that's why we recommend using a flat surface within that. But I guess the significant thing to understand is that when you're looking at, and I'll go into this in the API section, is that we actually, within the API, when the callbacks that are returned, distinguish surface reconstruction from the object reconstruction, or the prop reconstruction. And what we're doing there is we're returning a behavior, but also a set of meshes that you can apply custom rendering to, and also custom app logic to that. So you get a surface, and then you're also getting individual meshes for each of the objects or the props that are being returned. And they're being recognized uniquely. And the other neat thing about it is that, as I'd mentioned with a standard device camera, you need to bring in a known target. You have to have a ground truth reference of some sort. What a depth sensing camera is going to provide using smart terrain is the ability to estimate scale automatically. So really you're inferring both the dimensions of the objects and their physical arrangement, their geometric arrangement in the scene, automatically using that. And what it's doing is really coming back, and what you'll do in the environment is define a scene unit, and it's really returning each of the props and the surface area according to their area in that unit definition, basically. So what I'm going to show you here, this is a little bit rough because we just shot it the other day, but I'll show you a video that depicts smart terrain running on a standard device camera and then shows you the results using a depth sensing camera. And this comes off of the So this is our current version. As you can see, I need to pull back, and then as I move around, those black boxes are showing you the bounding box that's used to approximate the physical object. Now we've implemented a really simple, this is called beams. Basically what it's doing is just rendering the path of a point that's testing the depth across these surfaces. And as you can see, it recognizes the position of each of the objects, and it's able to actually trace the geometry of the bounding box that surrounds it. And again, this is available today. This is something you can get if you go to developer.vuforia.com. So here's an example running off of the Aquila device. It starts automatically. That mesh being returned is really the depth map that's coming back. You'll notice as I move around, it paints the side surfaces, and it can actually understand the interiors. So it's giving you a very, very close reconstruction of the physical surface. Now you'll see as the beams go over here, they're able to not they are able to understand, but the app logic is able to understand really an interior versus an exterior surface. And also you'll see that it's able to go into the cup, it's able to understand the edges of the table. And it's just generally much tighter than what you're getting out of a standard device camera. This view is with the depth map turned off. So you still have the ability to understand what the surface geometry is. We're just not showing the depth map being rendered. And again, you can see that it recognizes an interior versus an interior. So if I were to have gone around with that and actually closed off the surfaces, if I walked around the back of the table, you can create completely closed models of that. So with the vase and the box and everything else, they would be treated as a unique surface mesh with a closed surface, right? So it's not, it doesn't, the fact, I sort of ran that quickly and just captured the front surfaces of everything. So what I'm going to talk about now is really some of the considerations in developing using depth sensing, using smart terrain on a depth sensing camera. And what I'm going to address is the supported environments. Where can you run this? What user experience do you want to try to induce, and what are some of the considerations of the user experience? How to design content for smart terrain on a depth sensing device, and also how to manage meshes. And the significance of managing meshes is both to constrain the area of the experience that the user is going to be generating, but also because it's a memory management consideration. Large meshes are computationally intensive to handle, and so you want to have app logic that you're implementing that understands how many props have you reconstructed and how large of a surface area so that you're not bogging down the application. So supported environments really for a depth sensing device aren't so different from what we're supporting with a standard device camera. Again, you need consistent lighting, you need to avoid shadow, you don't want specular reflection, you don't want really visual characteristics that are removing features from the environment, whether it's features coming from the depth, or coming to the depth sensor, or coming from the optical characteristics or the contrast of the environment. And again, what we're recommending is that really due to the configuration of these devices is that, again, it's like a tabletop experience. You want to identify a visually discernible area. It's good to have a flat surface. And it's really in the range of, tabletop viewing experiences, near-range experiences. It's not something that I'm going to be reaching across a room with. It's really occurring in the nearer proximity of the user. And it's helpful also for the fact that the user needs to understand that they can capture the scene really with a subject matter that's identifiable to them, in a sense. So what you're saying is, look, stage a setting, put your props in the setting, and then you can move around that to perform reconstruction. But it isn't just an arbitrary experience. It's something that's actually defined. One of the other considerations with smart terrain using a depth sensing device is that with IR depth sensors is they tend to be sensitive to IR absorption. So what that means is that many of them are going to be, you're not going to get good depth registration on a black surface, for example. Black will absorb the light. Also, they're sensitive to very bright light. So both with smart terrain on a standard device camera and using a depth sensor, we tend to recommend them as in-home, I mean not in-home, but indoor experiences. It's also better for lighting consistency. And the other vulnerability, I guess, with the depth sensor is just the understanding that they're subject to IR noise. So if you're developing like a multiplayer IR-based game, that the IR sensors can conflict with each other, basically. They'll see the emission from the other sensor. As I mentioned, near-range experiences, visually distinct borders. Opaque surfaces, again, you don't want something that's mirrored, you don't want something that is see-through. And then stable room lighting. So for the consideration of designing content for smart terrain using a depth sensor, what you're getting out of this, again, is relatively tight, high-density meshes, both for the props and the surfaces. So you can apply different rendering characteristics to those. And also what you're getting, because you know the position of each of these, is that you can apply custom content to that object in itself. And what that means is that with this, you know the cup versus the book versus that tissue box, so that being that you can identify where they sit in the scene, you can attach models to them. Really, in using, or models or other rendering, but if you've worked with our stuff before, especially in the Unity environment, basically the technique for augmenting a situation like this is that you're making the augmentation of the media child of the object that's being brought in. And what that does is it brings it within the coordinate space of the object and enables it to be registered to that in the physical environment. And then the considerations for mesh management really are that you're getting a high poly mesh out of this, both for the surface and the object. And so what you want to do is keep account of the area of the surface and also keep account of the number of props that are being returned. This is a really basic consideration, but it's just a good practice when you're developing for this, knowing that, if you can look at let's say that you're developing an application, you understand on the device that you're targeting that you can support effectively 5 props in a surface area of a meter, then you can use that to understand how to control the life cycle of the smart terrain app. And as I get into the API, I'll explain exactly how that's implemented. So really the role of the smart terrain API here is that it's a universal API for depth-aware devices. And what this is, as depth sensing hardware becomes available and it's available in consumer devices to developers, is that the API that we implement is going to be consistent across both standard device cameras and any depth sensing hardware. So you'll be able to use really the same API call flow, the same life cycle, and the same sorts of callbacks in one context versus another. Now, I guess one of the considerations is to provide full portability for all hardware, because you're going to sensing characteristics that you want to handle as far as the user experience than you would for a standard device camera. So for the underlying API layer, you will have that portability, but as far as the user experience and some of the design considerations, you'll probably want to factor whether you're on a depth sensing device or you're in a standard device context. So as far as the smart terrain call flow, it's really very basic. What you're doing is when you want to initialize the experience, you're starting mesh updates. So there's a smart terrain tracker object that you're referencing. You start mesh updates on the object. Once that's begun, really the initialization has occurred, this is all automated. So you're going to begin on a frame-by-frame basis to get on-surface updates, callbacks. For any props that are created, any objects that are detected in the scene, you'll get on-prop created callbacks. When that occurs, what you're doing is deliberately associating a prop instance with a prop behavior, and the prop behavior is managing really the state of the prop in the scene. And then subsequently, for each update of the prop, you're being returned a prop instance. And when the prop is refined, meaning that refinement occurs if you have two objects that are close, it's seen as a single object, and as you move, it's understood as being distinct objects. It'll actually delete the original object and then return two new objects. So that's how the refinement of object occurs, basically. And then once you have all of this in, and you have basically you have all the props you constructed, you've determined that you've built the extent of the scene to as large as you want it to be, then you stop mesh updates. So it's really pretty basic. You know, I mean, that's 1, 2, 3, 4, 5, 6, about 7 calls that you can use to manage really the life cycle of the app and apply any of the custom event handling that you'd want to do. So just to review that, when you initialize the smart terrain scene, you're starting mesh updates, right? So that enables initialization. Meshes are going to start to be built. This will occur for for depth sensing devices, you're going to get meshes and props simultaneously, basically. So these aren't necessarily discrete steps. They're going to occur really within a few frames of each other. Again, with each mesh update, you're going to get an on-surface updated callback. With each prop update, you're getting an on-prop updated callback. And again, this is returning a prop instance. Both with the surface updates and the prop updates, you can use the instance that is returned to access the mesh that's associated with that. So you can actually drill down to the mesh, and that's where you're applying custom rendering on any of the meshes that are returned as artifacts. And again, once you've reconstructed the scene, you simply stop mesh updates. And it's really that simple. So what I'm going to do, this is just a summary of the same thing we've reviewed. I'll go into the Unity environment and show you really how a smart terrain scene is set up. And then what I'd like to do is I have the Aquila device here, and I'll actually give you a live demo of that. Just get this over here. Oops, hold on a moment. Is that going to pinch me? Huh. Can you possibly push it onto my primary screen? Just because I think it's going to... Oh, well, I'll go through this. Hold on one sec. Oh, just because it's splitting the screen, and I think it's clipping the clipping it a little bit. Okay, hold on one sec. Yeah, come on out. One second here. Yeah, can you? Let me see what the. Let's see. How do you push it onto the?
So you want to switch your primary?
Yeah, if we can just get it onto the primary. I think the.
Do you want to put it into clone mode or just?
We could just work off of that.
Can I minimize it?
Yeah, go ahead. There you go. Yeah, I think you got it. It's that one right there. Yeah. It's up there, actually. I think we're good, yeah.
Is that what you're looking for?
Yeah, I think we're all right. Is it going to show it? I think it's still off on the right-hand side.
Yeah, so you want.
What I'd like it to do is, yeah, if we can sit it here just so that I can get it framed properly for the,
Okay.
it's clipping the edges of the,
That window.
is it not letting you pull it over? Here, let me grab it. Let me see if I can get it.
We can switch that back if you want.
Now it's just, the weird thing is it's showing it on my desktop. Oh, you know what we just did is we pushed this onto the other.
Yeah, do you want to switch that back?
Yeah, let me get my proper desktop. So this, we're actually looking at the second screen now. I need to push it into here. We need this to be,
Yeah, just dragged them. I just switched positions. There you go.
into that.
And apply.
Okay. Now it's still doing it. See, strangely, it's showing it here and it's not.
Let's see. What if we tried? You think if we just cloned the image?
You know what I'll do? I'll just go into the demos. You guys want to see the demos? Okay, let's do, let's do that. We got like 15 minutes, so we'll hit those. Don't even worry about that, and I'll just, yeah, don't even worry about it. So what I'm going to do here is actually stage a scene using Smart Train for a standard device, and one of the things I'd like to do actually is pull this back because it's a very dark surface. And then I'll set it up on that. So again, one of the considerations in using Smart Train with a depth sensing device is, again, that IR absorbent surfaces can be a consideration. So let me get this out. Brought some props here. Now it's a little dim up here, so we may have some issues, but let's see if I can get it running. So this, change this out. I'm going to run it off of my Mac. Oops. You getting that? Okay, good. You guys see, John? Yeah, good. Okay. So this is the Aquila device, right? And what you can see on the back here is visible is that it has an IR laser, has a standard RGB camera, and then it has another camera to pick up the IR laser, so it receives it. It's the IR camera. But it basically has the laser, the camera, and then a standard RGB. This is a little bit dark for what I'm trying to do, but we'll just see if I can get you a decent. See if we can could you hold the camera while I shoot this, Liz? Just try to get it on the device face. Hold on one second. Can you see it? I know we're kind of MacGyvering this whole thing. So these devices are hot out of the oven, so we're not getting video off of them yet. But can you see that? So basically what's going on with this is that the IR laser is projecting against the surfaces, and it's going to try to, it's a little dark for what we're trying to do, but if I can get it, it'll actually start building a mesh off of this. I don't know that we have the light for the ability to do this. Hold on one second, let me reinitialize it. There are always demo gremlins when you get into this stuff. So. Yeah, so what should be happening here basically is that I think if we had brighter light characteristics, maybe after this we can bring up the lights and I'll show you guys live, is that what'll happen is that it's actually going to build out a mesh of the surface, of the white surface, and it'll start to build the reconstruction of these props in the setting. Unfortunately, I don't think that we've got the lighting to do it. So maybe after the session, if you're interested in seeing it, I'll see if I can get it running for you. That's it. Do you guys have any questions? No? It isn't available yet. You can get Tango devices. The Aquila isn't available quite yet, but I'm sure they're going to announce when it's available to developers.
Do you guys have any plans on doing object recognition for AR purposes?
We have an object recognition beta that's coming out. We're intending it for the fall. So it uses a somewhat different technology, but it is something that's coming into the market.
This year? Is it now or
Fall
fall next year?
next year. I'm sorry, our fall is really December. So it's going to be later in the year. Yeah. Okay, thank you.